Across the western United States, fault systems separated by hundreds of miles are beginning to force an uncomfortable reassessment of how seismic danger is measured. Beneath coastal forests in the Pacific Northwest, offshore trenches hidden under dark ocean water, desert basins in Utah, and fractured crust stretching across California, geologists are confronting a possibility that once sounded too improbable to seriously model. Could multiple major fault systems rupture in overlapping sequences? Could earthquake hazards once treated as isolated events actually be linked by timing, stress transfer, and geological synchronization? And if so, how prepared is modern infrastructure for a chain reaction extending across entire regions instead of a single state? A new body of research emerging in early 2026 has intensified those concerns. One study, developed over nearly a quarter century and centered on sediment cores accidentally collected off the Pacific Northwest coast in 1999, suggests that the Cascadia subduction zone and segments of California's San Andreas Fault may have ruptured in close succession multiple times in the past. At nearly the same moment this research gained widespread attention, a burst of seismic activity struck southern Utah, where more than 30 earthquakes rattled areas near Canosh within a single morning along the Intermountain seismic belt. The events were unrelated in mechanism, scale, and geography. Yet together, they reinforced a broader realization taking shape across American seismology. The tectonic systems of the western United States may be interacting in more complicated ways than emergency planning frameworks currently assume. For decades, earthquake preparation in the United States has largely depended on compartmentalization. California prepared for the San Andreas. Oregon and Washington prepared for Cascadia. Utah monitored the Wasatch Fault and volcanic fields scattered across the Basin and Range Province. Hazard maps divided risk into separate colored zones, each tied to specific faults and recurrence intervals. But Earth's crust does not obey administrative boundaries or planning assumptions. Stress moves. Plates interact. Sedimentary records preserve clues that modern monitoring systems have only recently begun to recognize. The Cascadia subduction zone stretches roughly 700 miles, or more than 1,100 kilometers, from Northern California to British Columbia. It marks the boundary where the small Juan de Fuca plate dives beneath the North American plate. Unlike California's San Andreas Fault, which visibly slices across the landscape with clear surface features, Cascadia remained deceptively quiet throughout recorded American history. No major rupture had occurred there since European settlement of the Pacific Northwest. For much of the 20th century, many scientists doubted the fault could even generate catastrophic earthquakes comparable to those seen in Chile, Alaska, or Japan. That changed dramatically during the 1980s and 1990s as evidence accumulated from drowned forests, offshore turbidity flows, coastal subsidence patterns, and Japanese tsunami records. Researchers eventually determined that Cascadia had unleashed a massive megathrust earthquake on January 26, 1700, producing a Pacific-wide tsunami that reached Japan without any locally felt quake there. The realization transformed the Pacific Northwest from a region considered moderately seismic into one of the most dangerous earthquake zones on Earth. Yet even after that discovery, Cascadia was still largely studied in isolation. The new research from Oregon State University and collaborating institutions challenges that separation. Its origins trace back to a geological expedition in 1999 involving sediment core sampling off the Pacific coast. Scientists studying underwater landslides and earthquake-generated deposits extracted long cylinders of seafloor sediment containing layered records extending back thousands of years. Within those cores were turbidity flow deposits, chaotic sediment layers created when intense shaking destabilized continental shelf slopes, sending underwater avalanches racing downslope. Initially, researchers focused on identifying the recurrence history of Cascadia megathrust earthquakes themselves. But over years of increasingly detailed analysis, an unusual pattern emerged. Some sedimentary disturbances appeared too widespread and complex to be explained solely by Cascadia ruptures. Certain event layers aligned suspiciously with known periods of large earthquakes farther south along California's plate boundary system. The possibility gradually took shape that some earthquakes may have occurred in geological paired sequences, linked seismic disasters separated not by centuries, but potentially by hours, days, or months. This idea remains distinct from the simplistic image of one fault directly triggering another like falling dominoes. Earthquake mechanics are far more nuanced. Large ruptures redistribute stress throughout surrounding crustal regions. In some cases, they increase strain on nearby faults. In others, they reduce it temporarily. Dynamic seismic waves can also disturb fault systems hundreds or even thousands of miles away, altering pressure conditions in critically stressed rock formations. The San Andreas Fault system itself extends roughly 800 miles, or nearly 1,300 kilometers, through California. Rather than a single crack, it consists of branching, interconnected faults accommodating the sideways grinding movement between the Pacific Plate and North American Plate. Northern and southern segments behave differently. Some areas creep gradually. Others remain locked for centuries while accumulating enormous strain. Researchers examining offshore sediment records found evidence suggesting that several major Cascadia events may have coincided surprisingly closely with earthquakes on portions of the northern San Andreas system. The statistical overlap exceeded what random chance alone would likely produce. In geological terms, the synchronization signals appeared meaningful enough to demand deeper examination. The implications are profound because the consequences of overlapping disasters would multiply far beyond the effects of either event occurring independently. A full-margin Cascadia rupture could produce an earthquake approaching magnitude 9. Coastal regions from Northern California through Washington could experience violent shaking lasting several minutes. Tsunami waves could strike some coastal communities within less than 20 minutes. Ports, bridges, fuel terminals, highways, electrical substations, rail corridors, and communications networks would suffer simultaneous disruption across multiple states. If significant sections of the San Andreas system were activated within the same broader seismic sequence, emergency response logistics could become severely strained. California serves as a major supply and transportation backbone for Western disaster response. Mutual aid systems assume unaffected neighboring regions can provide reinforcement, but synchronized seismic crises would undermine those assumptions. This concern has become increasingly important because modern infrastructure interdependence is far greater than during historical earthquakes of the past century. Electrical grids spanning multiple states rely on interconnected transmission corridors crossing seismic zones. Internet backbone routes and undersea cable landing stations cluster along vulnerable coastal regions. Fuel pipelines, freight rail systems, semiconductor manufacturing chains, and major ports form tightly coupled networks where disruption in one area can cascade across national supply systems. The Pacific Northwest alone contains critical infrastructure supporting trans-Pacific trade, cloud computing, aviation manufacturing, and energy distribution. California's ports handle massive volumes of imported goods entering North America. Simultaneous disruption to both systems would ripple far beyond the western states. Even without synchronized megathrust events, seismic complexity across the West has intensified attention in recent years. The Intermountain Seismic Belt, stretching from Montana through Utah into Arizona, represents one of North America's lesser-known but highly active earthquake regions. Unlike the plate boundary mechanics dominating California and Cascadia, the Intermountain West experiences crustal extension. The continent is slowly pulling apart in places, generating networks of normal faults capable of significant earthquakes. Utah occupies a particularly complicated tectonic environment. The Wasatch Fault system threatens densely populated urban corridors, including Salt Lake City, while volcanic fields and buried magma systems add additional geological variables across portions of the state. In May 2026, southern Utah experienced a sudden earthquake swarm near Kenosha. More than 30 measurable earthquakes occurred within a single morning, drawing attention from seismologists monitoring the region. Most were relatively small, but their clustering along structures associated with the Intermountain Seismic Belt renewed scrutiny of how strain migrates through Western fault systems. Earthquake swarms differ from classic main shock, aftershock sequences, Instead of one dominant large quake followed by smaller aftershocks, swarms involve multiple earthquakes occurring in clusters without a clearly dominant initiating rupture. Such swarms can result from fault adjustments, magma movement, fluid migration, or combinations of several processes. The Kanash activity also highlighted the volcanic dimension present in parts of Utah's geology. Ancient volcanic fields dot the region, and deep crustal heat flow remains elevated in sections of the Basin and Range province. Scientists do not interpret the swarm as evidence of an imminent eruption. However, the seismic activity underscored how tectonic and magmatic systems can overlap within the western interior. The broader significance lies not in any single swarm, but in the growing recognition that Western North America operates as an interconnected tectonic mosaic rather than isolated seismic provinces. Satellite geodesy, high-resolution seafloor mapping, improved paleoseismology, and dense seismic monitoring arrays have radically changed understanding of crustal behavior over the last 2 decades. Fault systems once thought dormant now show evidence of periodic activity. Hidden offshore structures continue to be identified. Ancient earthquakes are being reconstructed from sediment records with increasingly sophisticated precision. Along Cascadia's offshore margin, researchers continue mapping submarine landslides and fault scarps buried beneath layers of sediment. Deep sea cores preserve earthquake chronologies extending thousands of years into the past. Each newly analyzed layer refines estimates of recurrence intervals and rupture patterns. One major challenge involves determining whether Cascadia ruptures occur as full margin events or segmented earthquakes. Some prehistoric ruptures appear to have broken nearly the entire subduction zone simultaneously. Others may have involved only northern or southern sections. The difference matters enormously because earthquake magnitude, tsunami generation, and regional damage scale upward dramatically with rupture length. The possibility that stress interactions with California faults influenced some of these rupture sequences adds another layer of uncertainty. California itself remains under mounting seismic scrutiny. The southern San Andreas Fault has not experienced a major rupture since the early 18th century along some sections, meaning strain accumulation continues beneath heavily populated areas. Meanwhile, secondary systems including the Hayward Fault, San Jacinto Fault, and numerous blind thrust faults pose additional hazards. Modern urban expansion has increased exposure dramatically. Tens of millions of people now live across vulnerable regions of the West Coast and Intermountain West. Metropolitan infrastructure spreads across sedimentary basins capable of amplifying shaking waves. Water systems, hospitals, data centers, airports, and transportation hubs often intersect known fault zones. In Oregon and Washington, concern has intensified over structures built before modern seismic codes were implemented. Thousands of older buildings remain vulnerable to prolonged shaking. Coastal schools, bridges, and emergency facilities face particular scrutiny because tsunami evacuation windows in some communities may last only minutes. Tsunami modeling for Cascadia scenarios reveals alarming exposure patterns. Low-lying coastal towns could experience wave heights exceeding 100 feet or about 30 meters in localized areas depending on shoreline geometry and submarine topography. Ports critical to regional economies may become unusable. Saltwater intrusion and debris fields could complicate recovery operations for months. Farther inland, sedimentary basins beneath cities like Seattle and Portland can trap and amplify seismic energy. Similar amplification effects contributed heavily to destruction during earthquakes in Mexico City, Christchurch, and other urban basins worldwide. Compounding the danger is the issue of public perception. The synchronization research does not mean Cascadia and the San Andreas always rupture together, nor does it imply an imminent double earthquake is expected. Geological recurrence operates over centuries and millennia, not human political timelines. However, the evidence suggests that fault interactions may be more statistically meaningful than previously recognized. That distinction matters because probabilistic hazard assessments shape everything from building codes to insurance markets and emergency planning budgets. Seismic hazard models traditionally calculate probabilities for individual fault ruptures based on historical recurrence intervals, slip rates, and paleoseismic evidence. But interacting systems complicate those calculations. If one major rupture measurably alters probabilities on neighboring or even distant faults, hazard models must account for dynamic clustering rather than isolated events. Meanwhile, researchers continue refining the geological evidence behind fault synchronization patterns. Advanced radiocarbon dating, sediment fingerprinting, and offshore mapping techniques now allow scientists to correlate earthquake deposits with increasing precision. Turbidity flow layers, once viewed simply as evidence of local shaking, can now be compared across extensive submarine canyon systems spanning hundreds of miles. In some offshore regions, multiple canyon systems appear to preserve synchronized disturbance layers corresponding to major prehistoric earthquakes. Matching these records against terrestrial fault evidence in California strengthens the case for recurring temporal overlap between Cascadia and segments of the San Andreas system. Still, substantial uncertainty remains regarding exact mechanisms. Some scientists propose that large Cascadia ruptures may alter stress fields across western North America sufficiently to influence California fault timing. Others suggest broader plate boundary processes independently load both systems over long periods, increasing chances of coincidental ruptures without direct triggering. Dynamic seismic wave transfer, crustal fluid pressure changes, and viscoelastic mantle responses all remain areas of active research. Regardless of mechanism, the emerging picture is one of interconnected hazard rather than isolated fault behavior. If overlapping California ruptures compounded those impacts, national economic disruption would intensify substantially. At the same time, Utah's swarm activity serves as a reminder that seismic complexity is not confined to coastal plate boundaries. Interior western faults continue adjusting under continental extension forces that remain poorly understood in some regions. Buried structures invisible at the surface may still produce damaging earthquakes. The Basin and Range Province, extending across much of Nevada and Utah, contains countless faults formed as Earth's crust stretches and thins. Some move slowly over thousands of years, making recurrence difficult to estimate precisely. Others interact with geothermal and volcanic systems, capable of generating unusual seismic patterns. Historically, some of the West's strongest earthquakes occurred far from California's famous faults. The 1872 Owens Valley earthquake in eastern California likely exceeded magnitude 7.5. Nevada experienced multiple powerful earthquakes during the 20th century. Utah's Wasatch Fault remains capable of producing major urban disasters affecting the Salt Lake metropolitan corridor. As monitoring technology improves, scientists are detecting far more small earthquakes than previous generations could observe. Dense seismic networks now capture microseismicity, revealing hidden fault geometries and crustal stress evolution in remarkable detail. Yet increased detection also reveals how much remains uncertain beneath the continent. Ancient fault scars buried under sedimentary basins, offshore continental shelves, and volcanic deposits continue complicating hazard assessments. Some structures once considered inactive show signs of quaternary movement, meaning they remain geologically alive. Across the Pacific Northwest, earthquake drills, tsunami evacuation planning, and infrastructure retrofitting efforts have accelerated in recent years. Coastal communities install evacuation signage and vertical refuge structures. Schools conduct preparedness exercises. Engineers reevaluate bridge vulnerabilities and hospital resilience standards. But preparedness gaps remain extensive, particularly in rural coastal areas and older urban districts. And beneath all the planning lies a more difficult reality. Geological timescales do not align neatly with political cycles or funding priorities. Major earthquakes may not occur for decades, or they may arrive tomorrow. The uncertainty itself complicates public policy because societies tend to underinvest in disasters lacking immediate visibility. The emerging synchronization research challenges another deeply rooted assumption as well, that hazard zones can be treated independently for planning purposes. If Western fault systems interact more dynamically than once believed, then preparedness frameworks may need to evolve toward broader regional resilience models capable of handling simultaneous multi-state disruption rather than isolated catastrophe scenarios. Another growing concern involves the psychological effect of long, quiet periods along dangerous faults. human memory is short compared to tectonic cycles. Entire cities can rise, expand, and modernize during centuries of seismic silence, creating a false sense of geological stability. In Cascadia's case, more than 300 years have passed since the last full margin rupture in 1700. That interval has allowed massive urban development across Seattle, Portland, Vancouver, and countless coastal communities. Highways, ports, technology corridors, fuel depots, airports, and dense residential districts now occupy areas that experience catastrophic shaking and tsunami inundation in prehistoric events. The same pattern exists farther south. Portions of the southern San Andreas Fault have remained locked for so long that strain accumulation continues increasing beneath one of the most populated regions in North America. Modern skyscrapers, aqueducts, freight systems, and electrical infrastructure now span landscapes where prehistoric ruptures displace the ground by several yards or multiple meters in single events. Geologists are also paying closer attention to offshore faults once considered secondary hazards. Improved sonar mapping has revealed complex fracture systems beneath Pacific waters, including submarine landslides capable of amplifying tsunami generation during major earthquakes. Some underwater slope failures can displace enormous volumes of sediment, adding localized tsunami surges beyond the primary waves generated by fault movement itself. At the same time, emergency planners increasingly acknowledge that communication breakdowns may become one of the greatest obstacles during a large Western seismic crisis. Cellular towers, fiber optic lines, satellites, and electrical substations all depend on interconnected infrastructure vulnerable to prolonged shaking. In regions where roads, bridges, and airports sustain damage simultaneously, isolated communities may remain cut off for days or even weeks. Together, the emerging evidence from Cascadia, California, Utah, and the broader Intermountain West is reshaping how seismic danger is viewed across the United States. The challenge is no longer simply understanding individual faults in isolation, but recognizing how interconnected geological systems can produce overlapping crises across enormous distances, overwhelming assumptions that have guided disaster planning for generations.